Good evening. Let's wait 1 minute more, then we'll start the meeting. Okay, thank you for your response. I hope my voice is clear to you. Okay, let me project first question of today's assignment. This is the first question, as you can see on the screen. The silicon solar cell. Okay, thank you. These are the options. You have a silicon solar cell. Band gap is given to you. Silicon or something like, okay, whatever. Band gap is given, but 1.35 electron volt. The maximum wavelength for this perovskite solar cell. So here is a typo error. Let me correct it. So please solve this question. You have band gap. Yes, please. Are you getting right answer? Okay, so this is first question. Please try to solve. Okay, still calculating. Okay, no problem. Please solve. Okay, you have band gap. Ag is 1.35 eV electron volt. You have, let me recall you. You have conduction band, valence band, and conduction band. This is you have band gap. This is G. Now you have to find the maximum wavelength for this. This is type of perovskite band gap something. So that's why perovskite written. So you have to find the maximum wavelength. What is mean by maximum wavelength? Let me recall. hc by lambda. You have to find this max. Beyond this, let's say you have incident photon of the wavelength is lambda max. Beyond this maximum wavelength, your solar cell will not work. So you know band gap AZ is less than or equal to the incident photon energy. Did you know? If the energy of the incident photon is less than this band gap, your solar cell will not absorb the photons. So incident photon energy should be greater than or equal to. So maximum case is equal to. So just put in this equation you know in electron volt hc by lambda maximum. You have to find the max hc by 1.35 ev, and you know this value 12 volt 1.35. this is all unit will cancel out, this will you get in angstrom or nanometer. What? Okay, so solve this. This will be given nanometer, so unit will be in nanometer. Okay, wavelength okay. Your answer let me check also. 1240. Okay, 918 around. Yeah, you are correct. So this type question may be asked in exam, so you have to just focus. Let me ask other question. Let's say you have lambda of incident photon equal to whatever the answer is 950. Did this band gap will work for to absorb the photons? Yes or no? Please type in chat box. I am asking this. You have incident photon which is has lambda wavelength is 950 nanometer. You have band gap 1.35 eV. Did this band gap of material will absorb this incident photon? Can you find the energy of this? Please find energy of this incident photon. This is incident. Just 12.4 divided by 950. Please check yourself. You will get energy 1.305. So you have energy of incident photon 1.305, which is less than the band gap of material. So now this material will absorb the photon. Okay, energy is correct, but my question is that you have band gap 1.35 eV and incident photon energy has 1.305, okay, around eV. This electron can jump from conduction band, valence band to conduction band. As we discussed earlier, can this is possible? No. Okay, so at least we need that much energy. Higher energy will acceptable, but lower energy will not acceptable. At least incident photon should be in the range of band gap greater than or equal to. So please remember this concept. Clear to all? Clear? Let me give one more expose. Wait for. Let's say you have incident photon and light. Band gap, this is 1.4 and this is 1.35. You have incident photon energy. Let me give you. Let me give you energy. Incident photon from the sun has energy 1.36 eV. Same energy here, 1.36 eV. Which cell will work? Which cell will absorb this incident light? This is first, this is second. So as you know, only electron, this electron can jump if has energy, receiving energy is more than the band gap or equal to, at least equal to, should be maximum, but here energy is less than the band gap. 1.336 is EV is less than 1.4. This is incident, this is band gap. So incident photon energy should be more the band gap. Only electron can go from lower energy to higher energy. Clear? So this is concept, and you can find Einstein relation to find the energy relation, hc by lambda, or simple, if you put energy in electron volt, your lambda will should be in nanometer. Okay, with the help of this equation we can solve the numerical questions. Clear to everyone? Okay, let's move for next question then. The approximate thickness in microns of the observer layer in monocrystalline silicon solar cell is. If did you see the NPTEL lecture? Okay, what will be the answer according to you? Let's discuss. Answer will be in 300 nanometer micron. But how? As you know, monocrystalline silicon solar cell is indirect band gap. We have discussed in old lectures, old assignment. So it is optical absorption coefficient near the band edge is relatively small because of light penetration deeply into the silicon. A thick absorber layer is required to absorb most of the solar spectrum. So this is theory, but let's see the mathematical part. As we know, Beer-Lambert law, I equal to I naught, which is function of x e to the power minus alpha into x. X is the thickness of where light penetration depth into the material. So let's see, we have know the silicon has absorption coefficient is 10 to the power 2 or 3 per centimeter. So absorption length, we can directly, this is centimeter inverse, so just reverse this, is around 100 micrometer. So absorb the most photon, we have to absorb all the photons, so thickness should be greater than this thickness. So let's say thickness, most of thickness photons 2 to 3 time of absorber length. So that's why this is around 200 to 300 micrometer. Clear? So this is absorption of silicon coefficient. If we absorb the all photons, so thickness should be greater than the this absorption coefficient penetration depth, but not much more. If the thickness is higher, so recombination inside the material itself will happen, not the, let's say, centimeter. Like in micrometer is sufficient, but let's say we have proposed material which is thickness is centimeter. So centimeter thickness is used because our charge carrier diffusion length is not more, not having that much. So in the order of micrometer is sufficient to absorb the all photons, and after absorbing electron hole pair is generated and diffuse from respectively valence and conduction band. Extracted power from the solar cell can be maximized by, how we can maximize the power from the solar cell? With the help of minimize the sun's rays. So we have to maximize shunt resistance and minimize series resistance. How? Let's see in this picture. This is equivalent solar circuit. This is shunt, this is series, and this is diode. This is incident photon received by the solar cell. So wait 1 minute. This type you have JV curve or IV curve. This is voltage, this is current density on this y-axis. So this side, this tangent give you at JSC side shunt resistance. Inverse of this tangent you will get resistance, which is known as shunt resistance, while this side tangent inverse will give you series resistance. This is VOC side. Okay, so ideally solar cell curve should be look like rectangular. This is should be parallel to the x-axis and this should be parallel to the y-axis. So this side resistance slope inverse is give to you series resistance. So this type slope angle is 0, which is because parallel to the x-axis. Then slope is tan theta, which is theta is 0 here is 0, and inverse of slope will you inverse of this means 1/0 shunt resistance should be, this is infinite. So shunt should be infinite and series should be just angle is 90, then you will get opposite should be 0 for ideal. So maximize the shunt resistance and minimize the series resistance. If you want to good solar cell, shunt should be infinite or huge, while series resistance should be minimum or tends to 0. Clear? Please see these two curves. See large series resistance this side, this is large, this is medium, and this is lowest. So series resistance is increasing like that. And you can see shunt resistance, this is 0 parallel to the x-axis, this is increasing and this is also increasing, going up, slope is going up. Okay, so then shunt is reducing. We want to maximum shunt, please remember. So if you, let's say, you have first curve like that and you have like that curve, which is more central. Wait, this is not proper. This is original, but let's say you have like that curve. Which is higher shunt resistance? This is first, this is second. First or second? Which one is higher shunt resistance? And which is good curve for solar cell? First or second? Yes, please. Yes. So you have curve is parallel to the x-axis. Shunt should be parallel to the x-axis. And this is parallel line, but this is, you know, is a tilt toward the y-axis. So shunt is air is less as compared to this. Okay, so second is not good curve as compared to first. First is more preferable, which is showing the less defects. We will discuss these things. So here is series resistance, and series should be 0 and should be infinite. Please remember. And which side also remembers series and shunt. VOC side you will get series, and JSC side you will get shunt resistance. Okay, let me give you one question. You have a solar cell operates at I max, and you have series resistance. Okay, find the voltage loss due to this series resistance at maximum power point. Please solve this question. Very good. Other, please be active, please. You know, let's say maximum power point. Let's say this is IM, VM, then V equal to, you know, so you have series resistance RS, then V loss you will get at maximum. We have series at this point RS, so put the value. You have 4 amp and series resistance 5 ohm. This is in SI unit, so you will get the answer in SI unit. 2 volt V loss. Clear? This is simple solution. Okay, you have next question. Solar cell having band gap, let's say Ag1 and Ag2, which is Ag1 is greater than Ag2, are illuminated by one sun irradiation, then which of the following is expected to the true consideration only optical losses? You have this Ag1 greater than Ag2, then BOC is open circuit voltage, which give you more open circuit voltage comparison, and which is give more current density. Two options are correct here. Please. Okay, other please. Please see. Okay, check your answer. First see this curve. This is theoretical calculation. This is current density and this is open circuit voltage. This is curved like that. As open circuit voltage is increasing, current is decreasing, current density. You can see. So first thing you have to know why this is happening, why, how this is related to the band gap. Okay, so open circuit voltage is approximate VOC is Ag by Q minus loss term. This is give to you VOC. So VOC is directly proportional to the band gap from here. If band gap is high, then VOC will be high. So according to this, if band gap is first is higher, then VOC will be high. This is clear to all. First option. Then we will discuss the second. And see another one. But erase first. Short circuit current density depends the number of absorption photons. What is this? If you have higher photons, number of photon is maximum, then current density will be maximum. Lower band gap material absorb more photons, larger photon of. So wait, this for this I have to know. You know solar spectrum irradiation, one sun. Let me give you like that. This is lambda wave. This is in visible range. UV, NIR. This is irrad or power per centimeter square per lambda, like that. You know, this is a spectrum from the sun. So let's see, you have this is higher energy, this is less going to down energy. Let me give you two band gap material. This is Ag2 according to this Ag1, which is band gap is higher than, and this spectrum is incident on both cell, first and second. Okay, wait. Here is maximum, like that. One material is, let's say Ag2 is here, sorry, Ag1 is here and Ag2 is here. Got it? Because Ag1 is higher than the band gap. First, let's say Ag1 is higher and Ag2 here, according to this point. Okay, so this is this first cell, this first absorb only these spectrum. Got it? Only up to here, band gap. Beyond this will not absorb because energy is less from the band gap. Correct? And second will absorb from here, both first and up to here. So second one has more photons. From the spectrum which is available in one sun, while Ag1 has less as compared to second, which is absorbed by the respectively, so less photon present, while sorry, I have wrong, this is not less, this is second band gap, so this is more photons for Ag2, this is 2 and this is less. Got it this? So if you have maximum photons, you have more photons, you will get number of electron hole pair will higher. One photons will generate one electron hole pair. So let's say you have, here is 1000, let's say suppose, so 1000 electron and hole pair will generate. Let's say here is 100 only, so 100 electron hole pair will generate only. Here is 100, here is 1000, so 1000 electron give more current. As you know, number of current is directly proportional to the electron flow. How many electrons is there in the flowing? So more electron means more current density. Okay. Now see this explanation. This is JC dependent, the flux and with the energy depend on the number of the absorption photons, which is starting from the band gap to the infinity. Band gap to the infinity. This is easy to infinity. This is limit. Lower band gap material absorbs more photons. Lower band gap material absorb more photons, larger portion of solar spectrum. So Ag2 is higher, Ag1 is lower band gap according to giving you. So current density just will reverse, but so these are opposite. See, voltage is directly dependent to the band gap, but current density is just opposite, which is dependent to the solar ray spectrum. That's why current density is decreasing with increasing the band gap. Here, as is showing here. Okay, as band gap is increasing or BOC is increasing, current density will goes down like that. Now clear, or you have any doubt? Please ask if you have any doubt. If not, let's move forward. Shunt resistance in the solar cell can be increased by increasing dark saturation current, reducing defect density in the device, reducing non-radiative recombination, increasing the band gap. So shunt resistance is basically depend on the defects and non-radiative recombination, or more shunt resistance leakage path PN junction due to crystal defects, grain boundaries defects, pinhole. These are defects. Poor junction isolation, metallic shunts. To increase shunt, we must reduce leakage pathway. These are leakage pathways. So defects density, which is in B, reducing defect density. These are defects, which is responsible for shunt resistance, and non-radiative recombination also related to the defects. This is non-radiative recombination arise due to the defects in the material, shallow level or deep level defects, which is near to the band gap or mid SRH also. Non-radiative is not generate the photons, only via heat or phonon transition. Okay, let's move for next question. So yeah, let's say this is numerical question. You have solar cell as shunt resistance is 200 ohm and operating voltage is 0.6 volt. Find the leakage current through this shunt resistance. You can take for this question 2 to 3 minutes. Please solve now this question. Up to you. Yes, please answer as given. Yes, you are correct. So see the solution. This is divided by, or we know Ohm's law V equal to IR, or ISH can be written, we have to find ISH V upon R. Okay, so this is, we have to correct it. Okay, follow this. You have 0.6 volt and 200 ohm. Solve this, you will get the leakage sent current through the shunt resistance, or 3 milliamp. Okay, let's move for next. Why is network is too slow? Okay, you have, which of the following is correct for ideal curve for a solar photovoltaic device? This question we have discussed. This is not nothing, this is about by the series and shunt resistance. This side tangent give you reciprocal, this is J, this is B. Inverse of, as you know, this is y barabar x, let's say dy upon dx will give you tan theta, will give you slope. Similar way, dj by dv reciprocal of slope, you will, this side shunt resistance you will get, and this side also dj by dv series rs. Now please which option, which are of which first, second, third, fourth, or more than one option may be correct. Shunt should be infinite. Let me give me more, and this should be 0. This is VOC and this is at JSC. Or this point is V equal to 0, so V equal to 0 comma JSC, V equal to VOC and JSC equal to 0. This point is this. This is A point, this is B from here. Okay, so maximum, where should be the maximum shunt? This is v equal to 0. This is v equal to 0. At JC v should be 0. Short circuit current. So this is 1 because infinite cent v equal to 0. This point is this, and 0 we have to find out 0. V equal to V max or which one? BOC. Okay, so this is also equal to BOC. Any doubt now? No, then let's move forward. Which of the following statement is or are correct for the polycrystalline silicon in comparison to single crystal silicon? Very low light absorption, smaller carrier diffusion length are, you have to compare polycrystalline silicon as two single crystal. What are the advantages in the single crystal and what are the disadvantages in the polycrystal? So you have to compare these with respect to single crystal silicon. Okay, B and C. Yes, you are correct. Let me polycrystalline material, let's say you have order like that, so many grain boundaries, not in ordered, also randomly orientation of domains, so has many grain boundaries, more defects, single crystal means you have large crystal like that, no grain boundary, only one crystal, shape will be hexagonal. When we make single crystal, shape in the hexagonal. Or let's say this type. So less defects, here will be less defects. So as compared to this is more defects, higher defect density, and what else? Smaller carrier diffusion lengths. This is not the case. Better composition control, we can't say. Defect density low, no. This is smaller carrier diffusion lengths. This is not dependent on the, this is relatively dependent to the band gap and little bit on the defects. Primarily is band gap. So that's why B and C are correct. Okay, see the next question. In the top illuminated solar cell, light couple can be enhanced by, let's say you have solar cell, light is incidentating like that, solar spectrum from the top side. This is solar cell your. So top element light couple can be enhanced. We have to increase the coupling of light with the material. We have to increase number of photon absorption. Question is like that. How this? Making bottom layer thick, making top layer thin, using anti-reflection coating, texturing from at front side. So for that we have to just from top side losses due to the reflection. Reflection will happen here. So we can use anti reflection film here to increase more photon inside. Also we have to do texturing of this of the surface, which is also increase the photon number of photon inside is more, reduce the reflection losses also. You have to increase light from the top. From the top only reflection is from here at the top surface. So solution is anti-reflection coating and texturing from the front side. Next question, which of the following is favorable for efficient silicon solar cell? Yes, please. Anyone, please? Okay. B, C, and E. So from the lecture you can also see there is large diffusion length of the minority charge carrier, because minority charge carrier is only participate for the silicon for the current generation. Large built-in electric field. These are the correct. High optical depth for the radiation energy below the band gap. This is not below the band gap is not will work. Heavily doped based, heavily doped emitter. Doped base and heavily doped emitter. These are same options. base and heavily. Okay, lightly and heavily. Dop emitter and base. So these are not correct. When you see the making of PN junction, let's say this is base material, this is emitter side. If the doping is increasing, so recombination is also increases. So heavily dope will not give you more efficiency, while decrease the efficiency as well. Emitter should be more doping. The doping should be high as compared to base, but this is reverse, that's why it's not correct. This is also not correct. Which of the following strategies are adopted to improve the current collection top illuminate solar cell? We have already seen this type. We can also use this strategy, deeply buried contact, current collection, how we can improve the current collection. Heavily dope near contacts. Let's say we have, so doping here is should be more, because if impurity is there, defect is there, our electron will recombine with this impurity and lose the electrons, so current will less. Near contacts and deeply buried contacts. So this is, let's say you have contact like that, just touch, you have to just, this is only touch contacts, but this is buried, means inside the material we have to go inside to collect more efficiently. So these are the strategy to improve the current collection. The correct sequence of generate of electricity in the solar cell. Yes, please. This is the basic question of the solar cell. Which process how solar cell is work? Question is like that. What will happen inside the material? You don't know? Let's say you have material. First is incident of photons. After incidents, these photons absorbed by material if have energy is greater than or equal to the band gap of this material. Absorb, first is absorb, then create exciton. These excitons So your answer is correct. These excitons are dissociate. Dissociate means electron hole pair are goes to respective conduction and valence, let's say band. Dissociation of these excitons these excitons are known as electron hole pairs diffuse to charge carrier electrodes, then we can collect by respectively anode and cathode collection via charge carriers. Next question, the method adopted to reduce the surface recombination in the silicon solar cell is a surface recombination. So you can adapt surface passivation and more heavily doped near surface to the cell. Also, this is a strategy to reduce the recombination. Also, heavy, if you have heavily doped means impurity will less. Next question, which of the following affect the open circuit voltage in a silicon solar cell? VOC is dependent, doping concentration, minority charge carrier lifetime, intrinsic carrier concentration, band gap. Okay, band gap is correct. And what is a doping concentration also affects? What else? Intrinsic carrier concentration. All these all because of VOC is, you know, is dependent the band gap. Also Z naught, ln by Z naught, and J naught is dependent to intrinsic carrier concentration and also the doping concentration. Anything that changes the recombination or intrinsic concentration affects VOC. So minority charge also lifetime is important. Intrinsic carrier concentration also dependent. J naught current density is intrinsic carrier and doping density, let's say donor or acceptor, whatever. Also lifetime, tau, minority charge case lifetime. These are dependent to the band gap. All. Which of the following statement is true for polycrystalline silicon solar cell? Next question. Wait. Answer is giving to you also. B and D. Polycrystalline silicon solar cell. As we can see, grain boundaries act as the recombination center, and minority carrier lifetime generally shorter. In the polycrystalline silicon solar cell, we have already seen this question previous. So polycrystalline silicon consists of many small crystal grains, and these separate grain boundaries, which is strongly influence the electric property. Small grain means minority charge carrier tau is also low as compared to single crystal, and due to the grain boundary, your recombination center is also increases. So recombination increases. Wait means clear this question? Clear? Okay, thank you for your response. One minute. We have clear 14 question. Yes, next question. This is the reduced carrier lifetime in polycrystalline silicon is mainly due to. Yes, please. Let me give to you hint. Carrier lifetime in a silicon is mainly reduced due to the recombination center in polycrystalline silicon. These are from the metallic impurity. Polycrystalline silicon are often contain these are metallic impurity, iron, copper, nickel. Also, grain boundary, Denling bonds, structure disorder, defects. So these are acts at the recombination center, increase the center resistance. Now please give me the answer. The reduced carrier lifetime. This is tau. Polycrystalline mainly due to the metallic impurities also, and grain boundary defects. Grain boundary and metallic impurity. Next question. For a silicon solar cell, which statement are valid? BOC increase with the increasing light intensity. BOC increase logarithmically with photocurrent. BOC depend on the saturation current. Increase saturation current, increase BOC. BOC, how we can increase the BOC? Or decrease? What are the dependent factor? So let me give the answer. A, B and D, A, B and C, sorry, and C. VOC is dependent to the KT by Q ln. This is photon current, larger photon current, higher VOC. Okay, this is V naught, larger V naught recombination, lower VOC. Increasing I naught, decreasing VOC. So increasing with increasing light intensity. So this is I photocurrent related to this. If we increase the light intensity, photocurrent will be increased. VOC increasing with photocurrent. This is, let's say, A, B, C and D. Okay, 1 2 3 or whatever. This is log ln, log with photocurrent. This is also correct. VOC directly proportional to NL IPH photocurrent. And VOC depend on the saturation current. Okay, also this is VOC is ln upon I naught, inversely proportional to logarithm. Increasing saturation current, increasing VOC, no, this is I naught, and if this is increasing, VOC is decreasing. Clear? Clear? Are you there? Okay, thank you. Let's move for next question now. The reduction of the defect state at the grain boundaries in polycrystalline silicon solar cell is achieved by. How we can remove the defects at grain boundary in polycrystalline silicon solar cell? Hydrogenation, increasing vapor thickness, heavy doping, surface texturing. Grain boundaries not depend on the doping. Let's say you have these are the boundaries, these okay. So we can reduce these grain boundary. If you have hydrogen bonding like that with the other let's say NH2 with H, so hydrogen bonding with these and these defects get larger with the help of hydrogenation, will get higher. So we remove these, let's say merge two grain with one. So this process is known as hydrogenation. Doping will also impact only the material quality. If doping increasing, defects will less in the emitter side, let's say in emitter. This is also you give Answer means surface texturing only help with only surface. We have to inside the material grains, so many grains, grain and grain boundaries. So this is only helping on the surface, only remove the defects. Vapor thickness not will help, so only hydrogenation. Let's move for next question. For a equal doping concentration in a base region, which statement are correct? So answer is A, B and C. How movability of electron is higher as compared to hole, so that's why diffusion length will higher. So what is the this n type silicon is usually as better lifetime because mobility is higher, then lifetime of charge carrier also higher. Longer diffusion length, better collection. Heavy doping, Auger recombination increases, efficiency decreases. So according to this, n-type base generally give the higher minority carrier lifetime. N is higher than the P, that's why this. Electron diffusion length is larger than the hole diffusion length, also correct. And carrier collection probability increase with diffusion length. If longer diffusion length, better collection. Every dope which always improve efficiency, not decrease. Okay, let's. This is 18. Wait. Clear this question? Okay, so let's move for next. Hydrogen passivation in polycrystalline silicon solar cell helps too. We have seen this type question. Passive dangling bonds at the grain boundaries, reduce defect related recombinations, increase band gap, increase carrier lifetime, increase reflection losses. Okay, so polycrystalline will contain these type grain boundary. These are the defects. These are recombination center. Hydrogen passivation used to neutralize these electrically active defects. These are defects. So will help not on, this is your correct, but passivation dangling bond also at grain boundaries. Defect also reduce defect related recombination. A, B and D, not this is not dependent band gap. Increase the reflection losses, not this is inside. Increase the carrier lifetime. Hydrogen passivation give these advantages, please remember. Okay, see the next numerical question. You have a solar cell, delivered short circuit current density, you have JSC 10 amp and 1.5 illumination. Reverse saturation current, you have I0. The open circuit voltage VOC at 300 Kelvin, neglect the any internal resistance would be. You have to find open circuit voltage. These are the options. Please solve this. Let me give you VOC equal to KT by Q ln J upon J naught plus 1. This is the equation. Please find the answer now. You can take 2 minutes for this question. Or let me simple, FU current is higher, KT by Q ln J by J naught. This is simple. And this number is KT by Q at room temperature 300 Kelvin, 0.026 volt KT by Q. Now please solve. This is 10 ampere JC upon 10 to the power 12. Yes, please answer now. D please check again. What will be D? You have to take 10 by 10 to the power 12, which is 10 to the power 11. To use ln. This is not a log, this is ln. You have to multiply, convert to log. Now I am getting this number 0.658. What is your this number? This is around 25.328. Check this number. This is ln 10 to the power 11 just. Use calculator and this number is around 25.328. When you multiply 0.25.328 0.026. Now please check, are you getting correct answer, which is E 0.658. Just multiply. If you're getting 25.328, multiply by 0.026. I'm using calculator, just I'm getting this 25 multiplied by 0.026, you will get 0.658 volt. Okay, thank you. Now next question. Typical absorb layer, a single crystal solar cell absorb 50% the light intensity, light with wavelength 1100 nanometer thick incident from the AM 1.5 illumination. Assuming that the absorption coefficient for the front light alpha is given to you, the approximate thickness of the absorber layer is, you have to use I equal to I naught exponential minus alpha t. You have alpha 11 per centimeter, you have to find t, and absorption 50%, so I equal to I naught by 2. You have given 50% means half. Just put this number and now solve. This is, let's say, I by 2, 50%. This is I naught exponential minus alpha. This is, but please remember the units, 11, or let's say per centimeter into t. This will you get in centimeter. Or just take ln2 not ln, now ln will remove, and 1 by 2 is getting 2, minus minus cancel out, 11t. And 0.0630. Please check. Thickness, this is in centimeter because we have centimeter inverse. Are you getting? and you have to convert. This is micron, so 1 centimeter, you know, 1 centimeter, let's say 1 meter equal to 1 centimeter. Apply the conversion, then you will get 630 in micrometer. B. Clear? Okay, thank you. Next question. To improve fill factor in high efficiency silicon solar cell, how we improve, how we can improve the fill factor? Reduce series resistance, increase shunt resistance, increase surface recombination, use buried contact. 1 minute. Yes, please. Fill factor, you know, area under the, let's say this is rectangular and your other, so this is one with respect to red one, area of the above with respect to red one, rectangular one, is give you fill factor. So basically is dependent on this curve, so curve is also dependent on series and shunt resistance. So reduce series resistance should be 0, shunt should be infinite, increase reduce ND, use buried contact to get more current. Also you will get higher current, means like that JC is going down. Increase surface recombination, no, we have to reduce the surface recombination by anti-reflecting coating. Clear? And fill factor is defined and V maximum I max upon VOC and GSC. FF is depend strongly on resistance losses and recombination losses. Next question, for the better light absorption in indirect silicon, band gap silicon, base should be thick, emitter should be thick, surface texturing should be used, shunt resistance should be reduced. Sorry. So answer A and C. Base should be thick and emitter should be thin, and surface texturing should be used. Also we can use anti-reflection. So meaning optical absorption coefficient near the band is small, photon penetration depth is in the material, deep in the material, that's why base should be thick. To full absorption and texturing also improve the light absorb, reduce the recombination from the surface, that's why, but gets more photon inside the material. which of which method improve optical absorption in the silicon solar cell? Optically, how we can improve the optical absorption? Means optical losses should be less. Optical losses means recombination from the surface should be less. These losses should be less. Now please give me the answer. Yes, please. How we can reduce these losses? Reduce these losses via anti-reflection coating, surface texturing. Also, this photon thickness is not proper. This photon also transmitted. Incident, reflect and transmitted. Reflect and transmitted. These are the one. Okay. Last question. Which of the following technique helps to increase recombination losses in the solar cell? Please give me the answer. 1 minute. Which of the following technique to help reduce recombination losses? Sorry. We can use surface passivation and back surface field also. No series resistance. Recombination, if we increase the doping, recombination will increase. This is due to increase. Probability of the recombination will increase, occur when the photo generated recombination before the collection. To reduce recombination, reduce surface defects, improve carrier lifetime, repel minority carrier from the recombination active region. Okay, so this is last question. Thanks for your kind attention and actively participant. If you have any question, I can welcome. And next class not on Monday. I have to shift because I have to attend the symposium. So on Monday I will in travel. So probably on Wednesday you will get the email from the PMRF team. Wednesday. Next class will be on Wednesday, probably. Okay, so let's meet on next Monday with the 7th assignment. Thank you all. Okay, bye bye. Thank you. Let's close me the meeting.